Okay, and that's basically what leads us to HMACs. So HMACs are this hybrid between hash functions and MACs that have the properties of both. They're both collision resistant and they are providing integrity and authenticity. So HMAC, and it's very handy and very widely used. So it's basically both a MAC and collision resistant when the attacker has key K. And the way you construct it is something like this. So you take HMAC, key K, and the message M, and what you do is you basically output the hash of key K XORed with, I'm going to tell you what these pads are. So this is an outer pad. And then hash of key K XORed with an inner pad and XORed with the message. Okay, so we basically have two layers of the hash function. And the OPAD is basically 0x5c repeated, 5c multiple times in hex. And the iPad is 0x36 repeated. So why? Well, it's a bit of a technicality, but if you just had this hash by itself, so you wouldn't have the nesting of the hashes, then there's something called the length extension attack that we won't cover in class. But based on the construction of the hash, people are able to extend the hash with some extra bits, extend the message with some extra bits, and get the same hash. So they're able to find a collision in multiple constructions of the hash function, like SHA-1, for example. So that's why if you apply the hash twice, then you prevent those kind of length extension attacks. And you don't really need to understand, for this class, how those work. You can look it up if you want, but just for your own, so you understand why there are two different hashes intuitively, is because it's possible to do an extension attack if you have only one. And why this OPAD and iPad are these strange numbers? Well, all that's really needed is that the two keys are different to prevent these length extension attacks. So people chose these OPAD and iPad in particular. These would make these two keys different because the pads are different. But again, you don't need to know for the class as to how do those length extension attacks work. But what you do need to understand is the following. Why is this a MAC and why is this a hash, right? So why is this a collision resistant? Why is the HMAC collision resistant? Why is the HMAC collision resistant? So again, we are going to assume that H is a collision resistant hash. Why is this collision resistant? Right, exactly. So it's collision resistant because H is collision resistant, okay? So consider that I find, let's say, assume that I find an HMAC, I find two messages M1 and M2 that are for which the HMACs are equal. Well, because HMAC is a hash on the outer, right? So there's a hash on the outer. Then it means that the inner values have to be the same because otherwise you have a collision in this hash. And we assume that there isn't a collision in the hash function. So this implies that the inner side, so key and the OPAD, concatenate with the hash of the key and the iPad, concatenate with M1, implies that this is equal to key and OPAD, so the value from the second message, key and iPad concatenated with M2. All right, so then we can remove this part of the concatenation, so we're left with these two hashes being equal. But again, this hash function is collision resistant, so it means that the inside must be equal because otherwise it means you found a collision. So it means that K times the iPad concatenated with M1 is equal to K XOR iPad concatenated with M2. So this implies that M1 is equal to M2. All right? So basically this implies that, if ever two HMACs are the same, then it means that M1 is equal to M2. Yeah, that's a very good point. It's an annoying technicality that you can completely ignore. It's basically the reason that actually some hash functions were not secure against an attack that extends the message to the right. And they added this extra layer to protect against that class of hash functions. So it's an annoying technicality. Okay, you can assume that this hash is ideal for your understanding. It's really collision resistant. Yeah, SHA-1 and SHA-2 were having that length extension problem. SHA-3 doesn't have it. Yeah, it's a technicality you don't need to understand. But basically, this is the construction that's used in practice right now. Okay, so this is a great mechanism because you can use it both as a hash function and as a MAC. Okay, and without knowing the key K, then the attacker cannot forge the hash. Okay, again, it goes back to collision resistance. Because if he were able to forge the hash, then either he found the collision or he knew the exact input to the hash, but again, he doesn't know the key. Okay, so this is a really cool construction that you can use even in your project too, that provides you both MAC and hash at the same time.